here is a presentation for our MMAE 445 course in IIT. Our topic is Design and Analyze of V6 Engine. Here are 5 group members in this project. V6 engine is a V engine with 6 cylinders, which are become more common because of the reduced size, and which is adopted for medium-sized cars. Our project focuses on designation and assembly of V6 engine parts in Solidworks, tolerance and stochastic analysis of design parameters, and analysis of parts in Abaqus. Here is a list of all parts for V6 engine, and here is the assembled parts of V6 engine in Solidworks. We did 10 calculations in our project. In the original designation of V6 engine, it does not consider the manufacturing standard deviation. Our group project improved the manufacturing dimensions for practice by considering standard deviation. We assume that our manufacturing deviation is 0.1% and our target accuracy requirement is at 99.9% confidence level. There are mainly 2 types of calculations. Let's explain one each in detail. Let's take the calculation 1 as an example. The diameter of piston head R1 should be able to assemble into the engine block hole. Diameter R2 The manufacturing value of RA R1 should be 127.000 for 492 instead of 127. We also did the same calculation on engine block and shaft bushing, piston pin and piston head, rock arms and accessories, a symbol of rock arm and engine cylinder, air tube and air filter, bushing and retainer, air tube and engine side cover, piston rod and crankshaft. For the piston and crankshaft is another calculation type. 2 pistons rods should be assembled into the space of the crankshaft, but still leave certain space there, which means they are not assembled tightly. In our project, we also validated that when considering of standard deviation for manufacturing, the original design dimension still applicable for practice and no need further dimension improvement. Same calculations has been applied on camshaft and bushing.
Hi, my name is Amanpreet Singh. I am showing the following slides, and these are the analysis results of different parts of V6 engine run in the Abaqus. Part geometries are imported from Solidworks in IGES format. Materials are assigned to different parts after creating the section and assigning to respective regions. Meshing model of parts is generated. We have done 2 types of analysis, namely stress analysis and heat transfer analysis, so as to see whether the parts are structurally stable or not under different load conditions, and how heat flux change in nodal temperature takes place in high temperature conditions. These are the final analysis results for both types, that is stress and heat transfer, and this is the result for engine valve. Here material used is stainless steel. No type pressure is applied at the top surface, that is here, which is followed by rocker arm assembly. Fixed boundary condition is applied at the bottom end of the engine valve, that is here, fixed end. These are the fixed ends. Maximum stress value as obtained after running the analysis is found to be 19.25 Pascal, and permissible value for this material is 400 megapascal, which is way below, and so this part is structurally stable. These are the displacement results. and these are the stress analysis result of connecting rod. Upper surface of the connecting rod, that is this side, is fixed, and it is also fixed with the gudgeon pin, and this gudgeon pin is fixed with the piston head. The lower surface is connected to the crankshaft, which runs the wheel automatically, and here the load is applied at the upper portion of the inner surface, that is inside it is load is applied. Region shown in red color is the maximum stress region, and here the maximum value is found to be 6239 Pascal, and permissible value for this material is 250 megapascal. So we are good to go with this part. These are the stress analysis results for the piston head, and procedure followed is almost the same except the boundary conditions and the load condition. Here the compression pressure is applied at the top surface of the piston, and which I have taken to be 13 megapascal, including the factors of safety as 4. And the maximum stress value found is approximate to 12.123.0 Pascal, and maximum permissible value is way above, that is around 400 megapascal for the piston head, as this is a steel alloy. In this I have taken the value of Young's modulus at 200,000 Pascal and Poisson's ratio as 0.3. This is the analysis result for rocker arm spring, and procedure is almost the same except the bottom surface is fixed and the load is applied from the top end. These are the displacement at the different nodes for the rocker arm spring. Now here comes the rocker arm, and the material used is steel, and in this value of Young's modulus taken is 200 gigapascal and Poisson's ratio as 0.28. But here the rotation boundary condition is applied instead of fixed or encastrate boundary condition, and it is applied at the center hole where the small shaft inserts. Here rotation boundary condition applied with the small shaft inserts, and loads are applied at the 1.4 Newton and 2.2 kilonewton at the top and bottom end of this rocker arm, and maximum displacement as shown by result is found at the lower tip of the rocker arm. This is the crankshaft, and these are the stress analysis result of it. Here also the boundary condition applied is rotation boundary condition, and pressure of 10 Newton is applied on 120-degree surface of this crankshaft, as in practical reality the crankshaft is made to be like difference with each knob to be 120 degree, so as to correct the timing of the engine valves and the piston. And von Mises and displacement results of the crankshaft is shown, and maximum displacement is found at the middle knob. Now here comes the heat transfer analysis. In heat transfer analysis, the heat flux are considered as loads, and interactions are used to define convection and radiation properties. This is the exhaust manifold. In this, the first interaction is created to define surface radiation. Inside surface of this hollow pipe, this is a hollow pipe, and inside surface of it is selected. To define properties of outer surface, boundary film condition is selected and outer surface is selected. This outer surface is selected. Base and face of this hollow pipe, this is this base, and the face of this hollow pipe is selected to be fixed. But one thing to remember in heat transfer analysis, like we have to always give Stephen-Boltzmann constant and absolute temperature in Kelvin to be provided always. And these are the results. These are the heat flux and reaction flux of the exhaust manifold, and these are the nodal temperature results. This is a heat transfer analysis of oil pan, and fixed boundary condition is applied at the inside of oil pan, that is whole surface other than the top one, but this is the top surface I am including. And for the load, surface heat flux Heat flux was given by selecting the complete model. Nodal temperature values at different nodes for the oil pan. These are the heat transfer analysis on engine head. In this, body heat flux was given as a load condition. Opposite faces as taken as one set and applied radiation constraint. These are the opposite faces. This and this. This and this. And inside surface of engine head is supplied with the convection interactions. This is a surface. These are the result for the nodal temperature. Here also the load condition is applied as a body heat flux, and opposite faces, this and this, are taken as one interaction and provided as radiation constraint, and inside of it is supplied with convection constraints. So this is all with the analysis results. Thank you.